All right, so can everybody hear me?
Yeah.
Okay, so we only have one topic left in chapter 5, which we'll wrap up today. Okay, before I do that, let me just quickly give you an overview of what we've learned so far and just a view of where we are. So basically, we've learned, so I'll just explain this in one dimension. So, but the same thing applies in 3 dimensions as well. So the general program of mechanics is the following. The program of mechanics, the subject of mechanics is the following, that suppose at some initial time t equals 0, that could be, that time is not special at all. It's just any moment of time where you decided to press the button on your stopwatch and you call that t equals 0. You happen to know the position of a particle and the velocity of the particle, and those are x naught and v naught, right? Then the question is, at some future time t, are you able to predict what the position of the particle will be and what the velocity of the particle will be? So that is the whole idea. Can you predict the future? So if you're given the details, the information about a certain particle now, is it possible to figure out what that particle will be doing at some time in the future? What we've seen so far is that the answer is yes, as long as you are supplied this crucial bit of information. You're supplied the acceleration of the particle. If you know the acceleration, then it's entirely possible to go from the initial position and the initial velocity to some final position and final velocity, right? And at this point, it should be completely clear to you how to do this. We've seen this multiple times. If the acceleration is given as a function of time, then you have to use calculus, and you can just use integrals to go from to find the final position and the final velocity. And if the acceleration happens to be constant, then you can just use the kinematic equations and save yourself some trouble. But it's possible to figure out the final position and the final velocity of a particle if you know what the acceleration is. Now, the crucial question is, where would we get this acceleration from? So far, we have not bothered with this question at all in chapters 1, 2, and 3. The acceleration has always been supplied to us, right? Or we've been dealing with a situation where we know what the acceleration is and it's a constant acceleration like the free fall. So we already know what the acceleration is. So we've never really had to worry about where the acceleration, where we would find out the acceleration, because it's always been supplied to us. But still the question remains, where would you get the acceleration? The answer is, we began to see the answer once we got to chapter 4 and 5. The acceleration comes from this very crucial equation, F net equals mass times acceleration. This is the equation which determines the acceleration of a particle. And it basically tells you that the acceleration of a particle or a system is determined by the configuration of forces acting on that system, right? So force determines acceleration. And once you figure out the acceleration, you can figure out the state of the particle. You can figure out where, and if you know the initial state of a particle now, which means you know that's its initial position and velocity, you can figure out the final position and velocity at any future time using that acceleration. Is that clear to all of you? So that is the general program of mechanics. You're supplied the forces on a system. You use Newton's second law to find the acceleration of the system. And then using that acceleration, and the techniques of chapters 2 and 3, you can figure out you can figure out anything you want about the motion of the particle. That completely clear to all of you? All right, let's look at an example problem where we put this to use. So I'll give you a moment to read this problem. Okay, so what this problem is saying is that, okay, I'll just pull it up on my computer here. All right, so what this problem is saying is that there is a ramp and a truck is at the bottom of the ramp. We'll just ignore the dimensions of the truck like we always do, and we think of it as a point mass. The truck is at the bottom of the ramp, and the driver locks the brakes, so the truck is skidding, right? And so the truck starts skidding up this ramp. And there are on many highways in mountainous regions, there are ramps like this on the side of the road because trucks sometimes lose control. And so a safe way for the truck to stop if its brakes are not working anymore because the roads are too slippery is to just turn into one of these ramps, and then the truck can skid up the ramp and stop somewhere over there rather than falling off the highway. So that's what this is. So you've got this truck, you're given the mass of the truck, and you know its velocity. Its initial velocity is 35 meters per second. It's very fast. And it starts ascending this steep incline of theta. We'll just use a symbol here. Okay, it starts going up this incline, theta, and you're given mu s, and you're also given mu k. And the question is, how far will the truck skid before it comes to a rest? So how far will the truck go along the incline before it comes to a rest? That's what the question is asking. That makes sense? So what's its velocity going to be when it comes to a rest over here?
0.
Yes, exactly. That clear to all of you? All right. So we need to figure out that distance, like what distance is it going to cover before it comes to a stop? So how would we do this? Well, here we know the initial velocity of the particle and the final velocity of the particle. We have to find the distance, right, between these, the point where it had the initial velocity and the point where it had the final velocity. So this would have been an easy kinematics problem if we had known the acceleration of the truck as it was going up the incline. That makes sense? If you knew that acceleration somehow, you could have just used the third kinematic equation to find the distance between the starting point and the ending point. Is that clear to all of you? But the question is, we don't know what the acceleration is. So we can't immediately apply kinematics. But if we did know the acceleration, we could have solved this problem. Do all of you agree with me on that? All right. So what that suggests is, let's try to figure out the acceleration, right? So let's say that the truck is somewhere over here, and let's see if we can figure out the acceleration. How would I figure out the acceleration? Any thoughts on that?
Newton's second law.
Exactly. I have to use Newton's second law to find the acceleration. So that makes this a Newton's second law problem. Let's think about what forces are acting on this particle. So our goal is to apply Newton's second law and solve for the acceleration. So what are the forces acting on the truck while it's on its way up the incline?
Gravity and normal force.
Exactly. So gravity is one of them, and the normal force is the other one, Fn, right? And we've seen how you break up forces on an inclined plane. So you choose one direction, a direction parallel to the incline, and you choose a direction perpendicular to the incline. That's what makes it most convenient to break up the forces. And mg is, have we forgotten any force?
Friction.
Yes, there is friction, right? And which way is that, up the incline or down the incline?
Down the incline?
Yes. And how do you know it's down the incline?
Because slowing down.
Yes, exactly. Friction will always oppose the motion. It will never help the motion. That makes sense. So if the velocity of the object is up the incline, friction will slow it down, so that it must be pointed in the opposite direction. So there is a friction force which is acting in this direction. Can somebody tell me whether that's static or kinetic friction?
Kinetic.
Are you sure? What kind of friction is it?
Kinetic.
Kinetic friction, yeah. Is that what somebody said? I thought I heard static. Maybe you said kinetic. Okay. So, yeah. So a kinetic friction is what it is, because the truck is sliding. Its wheels are locked and it's sliding up the incline, right? So it's kinetic friction. Okay. So Fk is the friction force. And so now we have, so these are the three forces which are acting on the object. And so we have to apply net force equals mass times acceleration to get the acceleration. And then we can just do kinematics to get the final answer to the problem. So which force do I need to break into components here?
The force of gravity on the truck.
Yes, exactly. So we need to break up the force of gravity into two components, and one of them will be like this. And we know that this angle will be theta. So this component will be mg cosine theta, just as we saw yesterday. And this component will be mg sine theta. And we can forget about the original mg once we've broken it into components. So these are the forces broken into components. We just need a sign convention. You can choose any sign convention you want. We'll just go with upward is positive when you in the parallel direction. I mean, up the ramp is positive. And for this axis, we can just choose that direction as positive, right? Away from the ramp as positive. So now we have to write down Newton's laws, just as we were doing yesterday. F net equals mass times acceleration along our two axes, right? So let's do the perpendicular one first. Direction. Can somebody tell me what equation you get in the perpendicular direction? What do you get for F net in the perpendicular direction using our sign convention?
Fn minus mg cosine theta equals 0.
Very good. Fn minus mg cosine theta equals 0. This is correct, but how do we know that there is no acceleration in the up-down direction? I mean, in the perpendicular direction?
Because the car isn't floating off of the ramp.
Yes, exactly. Yeah. The truck has no tendency to fly off the incline or sink into the incline, right? So it's only moving along the incline. So there is no acceleration in that perpendicular direction. Okay, so we have one equation. Let's write an equation for the parallel direction as well. Can somebody help me write that? And make sure you're using the sign convention, which in our case is up the incline is positive.
Would that be negative Fk?
Very good.
G sine theta is
yes. Is equal to what?
Mass times acceleration.
Yes, exactly. Mass times acceleration in the direction parallel to the incline, and that is really the acceleration that we are after. That's what we are trying to solve for. That makes sense? Okay, so now we can solve these two equations and get the acceleration. Actually, we can just put in the formula for Fk. So our second equation becomes minus mu k times Fn. That's the formula for Fk. Minus mg sine theta equals mass times acceleration. And we are trying to solve for acceleration. Fn is the only thing that we don't know, but we can get rid of it using our first equation. Fn minus mg sine theta equals 0. So if you use that and plug that in, you get minus mu k times mg cosine theta. This part came from the first equation. Minus mg sine theta equals mass times acceleration. And now you can easily solve for the acceleration. All the m's cancel out. And so the acceleration of the truck up the ramp is minus g mu k cosine theta plus sine theta. I've just factored out the minus g just to be fancy. That's the acceleration, right? And what is the minus telling us? It's giving us the direction of the acceleration in our chosen sign convention. Our sign convention was that up the ramp is positive, and so we are getting the acceleration as negative because it's pointed down the ramp and it's slowing down the truck. That makes sense? So now that you have the acceleration, you can just do a kinematics problem and solve for the distance traveled along the ramp. Is that completely clear to all of you? So what you saw in this problem is the general program of mechanics being applied. We needed to answer a question about the kinematics of the truck. So we were given the initial position and velocity of the truck, and we needed to answer a question about at some future time, how far will the truck have traveled, right? We could have answered any question. The only piece of information we needed was the acceleration of the truck, and we went ahead and figured that out using Newton's second law. From the forces acting on the truck, we were able to figure out the acceleration. And so we found out the acceleration, and then we used kinematics to answer the question. Is that completely clear to all of you? All right, so as you will find out in chapters 6 and 7, this is a reasonable way of doing this problem, but it's not the best way of doing this problem. There are much more powerful techniques, which will get you the answer with a lot less work. We'll see that in chapter 6 and 7. But for now, this is the only way we know how to do this problem. All right, now, okay. So yeah, so for this problem, I noticed that it's clearer if I say the climber is at rest and is on the verge of slipping downwards. So I made that correction. So please make sure that you download the latest version of the PowerPoint. This without this word downwards, it becomes a bit ambiguous. But okay, all right. So let's talk about circular motion. So we've learned a lot of things about objects moving in a circle, particularly uniform circular motion. Can somebody again remind me what was uniform circular motion again? What's that? What does the word uniform signify?
It's moving in a circle with a fixed velocity,
Yes, fixed speed, exactly. That is uniform circular motion. An object moving in a circle with its speed fixed, right? So we've learned a lot of things about uniform circular motion. Let's just quickly review what we've learned. When we did that problem much in chapter 3, we saw that the velocity vector of the object is always tangent to the circle, right? And if it's uniform circular motion, the magnitude of the velocity is going to be fixed. So the speed will be fixed and the velocity vector will be directed tangent to the circle. What did we learn about the acceleration of the particle executing uniform circular motion?
It's always pointed inward towards the
Yes, exactly, towards the center of the circle. And there is a name for that acceleration. Does anybody remember what that name is?
Centripetal acceleration.
Centripetal acceleration, exactly. Does anybody remember what the formula for the centripetal acceleration is? If the magnitude of the speed is v, the radius is r.
v squared over r.
V squared over r, exactly. So when an object is going around in a circle with uniform circular motion, there has to be an acceleration that's pointed towards the center of the circle, which is called the centripetal acceleration. And in fact, that centripetal acceleration is responsible for keeping it on that circular path, right? So that's why the centripetal acceleration is essential. And we calculated that the centripetal acceleration would be v squared over r. This formula, we derived this for the case of uniform circular motion, but this formula is generally true. So even if it's not uniform circular motion, even if the speed of the particle is changing as it's going around in the circle, this formula will still be true, except that you'll have a different v at different points along the circle. So the centripetal force will be different at different points. I mean, the centripetal acceleration will be different at different points on the circle. So you can still use this formula, even if v is not constant. All right, so now let's consider this. So an object is if an object is executing circular motion, we know that there has to be a centripetal acceleration, which is an acceleration that's pointed towards the center of the circle, right? Where is this acceleration coming from? The answer is there has to be some kind of force which always points towards the center of the circle. That force is what is supplying that acceleration. That makes sense? Acceleration is always supplied by some kind of force. So if we know that an object going around in a circle happens to have an acceleration directed to the center of the circle, that immediately implies from Newton's second law that there must be some force or some combination of forces which is directed towards the center of the circle, and that is what's causing the centripetal acceleration. That makes sense? So let's look at an example. Suppose you have, let's consider an example of circular motion. So suppose you have, you take a stone or something and tie a piece of thread around it, and then whirl the thread whirl the stone in a circle. So your finger is at the point O, and you're whirling the stone in a circle like this. All right. So that's an example of circular motion. So in this case, what is the force that's directed towards the center of the circle at all times?
The acceleration.
The acceleration.
The force. What is the force? What kind of force is there? So the forces that we've seen are friction, normal force, tension. These are some of the, yes, go ahead.
Tension.
Yes, the tension of the cord is a force that is always pointed, acting on the object and always pointed towards the center of the circle. That makes sense to all of you? So we've discussed how when you have a stretched cord, there are at the two ends of the cord, you've got two tension forces which prevent you from stretching the cord. So there's also a tension force here, but that's irrelevant. We are only concerned with the force that's acting on the object that's going around in a circle. So you can see that there is a tension force which is always acting on the object and pointed towards the center of the circle. So this force is what provides the centripetal force in this case. So tension in this case provides the centripetal force. Centripetal acceleration, I mean. Is that clear to all of you? Let's look at another example similar. Suppose this is the sun and here is the Earth orbiting the sun. In this case, which force is responsible for providing the centripetal acceleration? In other words, which force is acting on the Earth and always pointing towards the center of the circle?
Gravitational force?
Yes, exactly. The gravitational force is always going to act in the line joining the Earth and the sun and pull the Earth towards the sun. So gravity provides the centripetal acceleration. Centripetal acceleration. Now, by way of terminology, whichever force or combination of forces provides the centripetal acceleration. In other words, whichever force or combination of forces is directed towards the center of the circle at all times and is responsible for keeping the object in its circular path is called the centripetal force. Petal force. But I don't like this name very much because it's a bit confusing. Because whenever we talk about a force, the forces that we've seen so far are tension, gravity, normal force, friction. These are real physical forces. They actually exert pushes or pulls on an object. Whereas the centripetal force is not an actual force in the sense that it's a role that can be played by some force. That makes sense? So it's not a real actual force, but it's a role that can be played by whatever force is relevant in that situation. So in the case of the planet, the role of the centripetal force is being played by gravity. And in the case of the stone being whirled around by a rope, the tension is playing the role of the centripetal force. So please remember that centripetal force is not an actual force, but it's a role that can be played by any force. That makes sense to all of you? Okay, so in this question, okay, let's look at another example. Suppose you have this circular track and a car is being driven along the circular track. So we are just, we can just see the top of the car. So the car is going in this circular track. And let's say that the radius of the track is r and the velocity of the car is v. Okay. All right. Now, in this case, since the car is going in a circular track, there must be some centripetal acceleration. Which force is providing the centripetal acceleration, do you think? Can you think of any any force that's acting on the car and is always pointed towards the center of the circle?
Would that be friction?
Yes, exactly. The friction between the tires and the road in this case is pointed always towards the center of the circle. And would you say it's static or kinetic friction?
Kinetic.
Anybody else want to try that?
Is it static because the car isn't really slipping?
That is correct. So this is a bit subtle here, but the friction involved in this case is static friction. Let me just quickly explain why it's static friction. So just imagine one of the wheels of the car, right? And let's label 3 points. Let's call this point A, this point B, and this point C. All right, and the wheel is rolling in this direction. Yeah, it's rolling in this direction. So right now, the point A is in touch with the ground, and B and C are, okay, let me put B and C over here. Yeah, it's better. So B and C have not yet touched the ground, right? Do you see that the point A is not really sliding against the ground? Momentarily, the point A is at rest. just for one moment, right? The very next instant, what's going to happen is that the wheel will have rolled a little bit, and point A will come up here. Point B will be now touching the ground. Point C will be about to touch the ground. Now, once again, point B is not really slipping against the ground. It's momentarily at rest. That makes sense? So as the wheel rolls along, the point that's momentarily in touch with the ground is not slipping against the ground. It's just momentarily at rest, right? But just for one moment. The very next instant, the wheel will roll a little bit more, and then point C will be in touch with the ground, and points B and A will be will have moved. So you can see that every point that's in touch with the ground is not slipping against the ground. It's instantaneously at rest. So this kind of rolling is called rolling without slipping, and we'll talk about it a lot in chapter 10, rolling without slipping. And that is the reason why the friction is static friction. That makes sense? If the tire were skidding against the ground, then the point that's in touch with the ground would be sliding against the ground, right? But that's not what this tire is doing. It's just rolling normally, rolling without slipping. So when it's rolling without slipping, every point that gets in touch with the ground is momentarily at rest. That's the definition of rolling without slipping. And most rolling is rolling without slipping. So that is the reason why the friction involved here is static friction. That clear to all of you? All right, so here static friction provides, static friction plays the role of the centripetal force. So hopefully it's clear to you that centripetal force is not a real physical force, rather it's a role that can be played by any real physical force. That makes sense? Just like Vanderbilt student is not the name of any particular student, right? Unless there is a student whose first name is Vanderbilt and last name is student. But Vanderbilt student is actually a role that's played by you guys, any of you guys, right? So centripetal force is just like that. It's not an actual force, but it's a name of a role that can be played by any force. That clear? All right. So if an object is executing circular motion, there must be a centripetal acceleration, as we have seen in chapter 3. And this implies from Newton's second law that there must be some force or combination of forces in the radial direction. And this net force in the radial direction is called the centripetal force. Is everybody clear about that? Okay. Yeah, and I made this point that centripetal force is not an actual physical force. It's a role that can be fulfilled by a variety of different forces like gravity, friction, tension, electromagnetism. These forces can all act like a centripetal force, right? Okay. So how do you analyze circular motion using Newton's second law? The method of analysis is exactly similar to what we've seen before. So what you do is you have an object that's going around in a circle. Let's actually work with a real example. So suppose you have a stone that is tied to a rope, and the rope is fixed at point O over here. The end of the rope is fixed at point O. And our stone is being whirled in a vertical circle. So it's going around in a vertical circle. So this is a vertical circle. Radius of the circle, let's say, is R. Okay, and the stone right now is over here and it's going this way. So it's going around in a vertical circle in a counterclockwise sense, right? So what we want to do is we want to apply Newton's second law to this stone. And the way we apply it is exactly the same as what we did all day yesterday, with just one or two minor differences. So let's analyze. So we're going to follow the same steps for applying Newton's second law here. So let's choose our system. Our system is clearly just the stone. What are the forces acting on the stone as it goes around in a circle?
Tension going inward.
Yes. So one force would be the force of tension, which is going this way. What other force is acting on the stone?
Gravity.
Gravity. Very good. Any other force, or is that it? Would it be correct to say that there is also a centripetal force acting on it?
No.
No.
Tension?
Yeah, we've already taken the tension. Tension and gravity we've already considered. It's not correct to say that there's also a centripetal force acting on it, because centripetal force is not really a force, it's just a role, right? So when we are talking about the actual physical forces acting on this stone, there are only two, the tension and gravity. And there could also be air resistance because it's going through the air, but we are not going to bother with that, right? So as far as we are concerned, it's tension and gravity. That clear to all of you? So we've identified the forces. Now we need to choose our axis and sign conventions. And this is the only place where this analysis is a little bit different from what we've seen before, because there is a very convenient choice of axis that you can use. Now you can choose any axis you want. Your physics doesn't really depend on how you make your choice of axis, but some choices of axis make your analysis very simple. And here is one of those places where you can make a really good choice of axis. So the very good choice of axis for circular motion is you choose one axis in the radial direction and you choose another axis in the tangential direction. So if you choose these axes, then your equations will become a lot simpler, right? Okay, so that's the only thing. And with these axes, there's also a very good sign convention that goes with these axes, which makes your life very simple, which only really applies to the radial direction. So the sign convention that we use is, okay, so let me just write these down. So you choose axis in the radial and tangential directions. And there is a sign convention for the radial direction, which is inward is positive. Radially inward is positive. If you make that choice, then it just makes your equations a lot simpler. So radially inward is positive. For the tangential direction, you can choose any sign convention you want. It doesn't make a difference. Is that clear to all of you? Our axis and sign conventions. All right, so with that, this problem is not any different from the problems that we did yesterday. So now let's go ahead and break. Which force do we need to break into components here?
Force of gravity.
Gravity.
Gravity, because tension is already along one of the axes. So gravity is the one that we need to break into two components. And let's say that this angle right now is theta. Let's say we are told that the rope makes an angle theta to the vertical. That would mean that this angle is theta. So what is the radial component of mg going to be?
mg cosine theta.
Yeah, the component that lies on the angle is always your cosine component. So this is mg cosine theta. And the tangential component of mg will be mg sine theta. Is everybody clear about that? Right. All right, so keeping our sign convention in mind, can somebody so what we're going to do now is we're going to write down F net equals mass times acceleration for each of our axes, as we all day yesterday. So what is the F net going in the radial direction? Keeping our sign convention in mind.
T minus mg cosine theta.
Very good. T is radially inwards. So that means it should get a positive sign. Mg cosine theta is radially outwards, so it should get a negative sign. T minus mg cosine theta is equal to mass times what?
Our acceleration, just our acceleration.
Yes, and what kind of acceleration does it have in the radial direction?
Centripetal acceleration.
Exactly. Is that clear to all of you? So when an object is going around in a circle, in the radial direction, it must have the centripetal acceleration, right? So along the radial direction, the acceleration is going to be AC. And if we are also given the speed of the particle, if we are told that the speed of the particle over here happens to be V and the radius is R, then we can also figure out the AC. We can just plug in V squared over R. Let's say we are given the speed of the particle at this point. We are told that its speed is V. So that would mean that the centripetal acceleration is V squared over R. And this equation becomes T minus mg cosine theta equals m v squared over r, if we happen to know the speed at that point. That clear to all of you? Okay, for completeness, let's also write down the equation in the tangential direction. So for the tangential direction, we need to choose a sign convention. You whatever you want it. There is really nothing There's no special direction for this tangential axis. So you can choose this direction to be the positive direction. So can somebody tell me what equation I get in the tangential direction? What is the F net in the tangential direction?
Is it tension minus mg cosine theta?
The tangential
Oh, in
direction,
the,
not the rate.
tangential
Yeah.
direction, sorry.
Yeah.
Is it just mg sine theta?
Yes, that's the only force that's in the tangential direction. That makes sense? That's all. So that's all that we get for F net. And that is equal to mass times whatever acceleration there is in the tangential direction, which is, let's just call that A tangential, AT. That makes sense? So if you were interested in finding what acceleration that it has in the tangential direction, you could have used this equation. In fact, you can get it right now. The m's cancel out, and you get AT is equal to g sine theta. That makes sense? So there is an acceleration in the tangential direction as well, in addition to an acceleration in the radial direction, right? Would you say that this particular particle is executing uniform circular motion?
No.
No, because you know that it's like when it's over here at the point shown, it will be speeding down until it gets all the way to the bottom, speeding up until it gets all the way to the bottom, right? And then when it goes up again, it's going to start slowing down. So its speed is changing as it goes around in the circle. That makes sense? On its way down, it will keep speeding up, and on its way up, it will keep slowing down, right? So, so this is not uniform circular motion. And you can also see that it's not uniform circular motion from the fact that there happens to be an acceleration in the tangential direction. So that acceleration will speed up the particle or slow it down, depending on how it's oriented. For uniform circular motion, you don't have any acceleration in the tangential direction. You only have one acceleration in the radial direction, which is the centripetal acceleration. That clear to all of you? Okay, so so that is how you analyze circular motion. You write down, you choose these special axes, one in the tangential and one in the radial directions. You write down Newton's second law in the radial direction. And if necessary, you also write down Newton's second law in the tangential direction if you want to find the tangential acceleration. And that's it. So that's really all there is to circular motion. Now, a couple of conceptual issues. So, okay, so you choose axis along the radial and tangential directions, as I said. And for the radial direction, it's very convenient if you choose this sign convention. Radially inward is positive. And let me just clarify one other thing here. When we wrote down our radial equation here, and I did m times AC, what sign should I give AC, the centripetal acceleration?
Positive.
It should always get a positive sign. And that is because the centripetal acceleration is always directed radially inwards. So that's one good thing about this sign convention. The direction of the centripetal acceleration is always positive, right? Okay. So Newton's second law in the radial direction becomes F net is equal to mass times centripetal acceleration, which is mv squared over r, as we just saw, right? Okay. So we did this example of a particle going around in a vertical circle. Let's do one more example of this. Let's look at the car on a circular track and just do the same thing just for practice. So suppose I have this circular track, and there is this car which is going around in a circle in a counterclockwise direction. So the car's velocity over here, its instantaneous velocity is v. Radius of the circle described by the car is, let's say, capital R. Okay, and the mass of the car is m. All right, let's apply Newton's second law to this car, right? So what are in the horizontal plane, what are the forces acting on the car? Just in the horizontal plane. We don't care about the weight or the normal force.
Friction.
Yes, and is it static or kinetic friction?
Static.
Static friction, exactly. So the static friction must be pointed towards the center of the circle, right? And that static friction is providing the centripetal force. So can somebody help me write down Newton's second law? So we have, this is the tangential direction, and this is the radial direction. So in the radial direction, and the car is moving at a fixed speed. Let's just assume this is uniform circular motion. So the car is moving at a fixed speed. So in the radial direction, what equation do I get for Newton's second law? F net equals mass times acceleration. Keep our sign convention in mind.
Fs is equal to mass times the centripetal acceleration.
Very good. Does everybody agree with that? Fs is the only force in the radial direction. So that's what all that goes into F net is equal to, so this is the radial direction, mass times the acceleration of the car, which must be the centripetal acceleration, right? That clear? And what's the formula for centripetal acceleration? It's v squared over r, right? So this is the equation that you get. The static friction force is equal to mv squared over r. V is the speed of the car. Everybody clear about that? Okay, now this quantity, mv squared over r, is a measure of how much force the agency responsible for providing the centripetal force needs to provide in order for the car to be able to stay on this circular path at this particular speed, right? So in this case, suppose the car has a mass of 1000 kgs. The velocity of the car is 10 meters per second, just to keep the numbers simple. And the radius of the car, radius of the curve that it's negotiating is maybe 10 meters. That makes sense? So in that case, how much force must be provided by friction? So you can calculate that easily from here. It's going to be 1000 times 10 squared divided by 10 newtons, which is going to be 10,000 newtons. So what that is telling you is that the friction has to be able to provide 10,000 newtons in order for the car to be able to stay on this track at a speed of 10 meters per second. That makes sense? That's the amount of force that friction has to be able to provide. Suppose the maximum force of static friction in this case, Fs max, which is mu s times Fn, suppose Fs max happens to be 23,000 newtons. Is the car safe? Absolutely, because all we need is 10,000 newtons. Friction can easily provide 10,000 newtons if the maximum force of static friction is 23,000 newtons. That makes sense? But suppose right over here, there is an oil slick. And the oil slick will change the coefficient of static friction, right? And so let's say this time over the oil slick, Fs max happens to be only 9,300 newtons, 9,300 newtons. So is the car going to be safe over the oil slick? The answer is no, because in order to maintain that speed over that particular curve, the car needs at least 10,000 newtons of centripetal force. And friction will not be able to provide that, because the maximum that friction can do over the oil slick happens to be only 9,300, right? So what's going to happen is that the car will not be able to continue over that, but continue along that circular path. It will just slide off. That clear to all of you? What, in order to be safer, what could the driver do in order to be safer?
Slow down.
Exactly. If the driver slows down, the V is going to go down, right? And so in mv squared over r, you will need, that will be a lesser number of newtons, smaller number of newtons. And that might be something that the friction can supply. That makes sense? So if the driver slows down, then there is a chance that they could safely go over the oil slick. But at the same speed, they'll not be able to go over the oil slick. Is that clear to all of you? So mv squared over r is a measure of how much force is required, how much centripetal force is required in order for an object to be able to stay on that curve at that particular speed. Is that completely clear? All right. Okay, so if the agency is providing centripetal force, can supply this much centripetal force, mv squared over r, then the object will stay on that circular path. If not, the object will no longer stay on that circular path. And I would recommend watching this video It doesn't really show up very well on Zoom, so I'd recommend watching it on your own. Okay, I show it in class usually. All right, 1:55. Let's take a break, and then we'll do a couple of example problems. 1:55, 2 o'clock is when we'll resume. All right, so let's get started. Let's try this problem. Okay, so I'll give you a moment to read this. All right, so what this problem is saying is there is this Ferris wheel, which is moving in a vertical circle of radius r with a constant speed v. And there's a passenger on the on the wheel who's going around in a circle with the wheel, and it's going to be at a uniform circular motion because the wheel is moving with constant speed v. All right, so so let's draw the wheel, and okay, I'll just draw it over here. All right, so this is a circular wheel, and here the passenger is in this position and also in this top. Let me just draw a nicer circle. All right, that's somewhat better. Okay, so the passenger is over here and also over here, and the seat stays upright the entire time, and the passenger is sitting. Okay, so what we have to find out is, so I'll just draw the passenger here as well. The wheel is moving with a constant speed v. So that's the speed of the wheel. So it's uniform circular motion. You have to find the force that the seat exerts on the passenger at the top of the circle and also at the bottom of the circle. So let's start with the bottom of the circle. Let the center of the circle be over here, and the radius of the circle is r. So we have to find out the force exerted by the seat on the passenger. What force is that? Which force are we talking about here?
The normal force?
Yes, the normal force. The passenger is sitting down on the seat, so the seat exerts a force on the passenger perpendicular to the surface. So the normal force is really what we're looking for here, right? Let's apply Newton's second law to the person. So our system is the person, and what are the forces acting on the person or acting on our system?
The normal force and gravity?
Yes, the weight of the person acting down, mg, and the normal force exerted by the seat, Fn. That makes sense? These are the only two forces acting on the person in this position. All right, so let's write down Newton's second law in the radial direction. So what was the sign convention that we use in the radial direction?
Inwards is positive.
Radially inward is positive, exactly. So in the radial direction, which is this direction, can somebody help me write down Newton's second law? So F net, so we are doing the bottom position. F net equals mass times acceleration. So what do I have on the F net side, the left side of Newton's second law?
The normal force minus your mass times gravity is equals.
Yeah, Fn minus mg is all that we have on the left side. Then on the right side, what is the acceleration? What should I put in for the acceleration? Mass times?
Centripetal acceleration.
Exactly. That clear to all of you? The person is going around in a circle, right? So they have to have a centripetal acceleration, which is v squared divided by r, r being the radius of the circle. That makes sense? So now you can solve for Fn. So Fn will be equal to mg plus mv squared over r. Is that clear? Okay. If you want, you can also write this as factor out the m, g plus v squared over r. And that is F net, that is the normal force, sorry, at the bottom, right? Let's do the same calculation for when the passenger is at the top of the circle. So once again, what are the forces acting on our passenger now at the top of the circle? And just think of the passenger as a point mass, just ignore any spatial dimensions. So what are the forces acting on our system at the top?
Normal force and mass times gravity again.
Exactly, the same forces. So the gravity will always be acting down, and since the person is sitting on the seat will be exerting a force in the upward direction. So can somebody help me write down Newton's second law for the top position?
Be mg minus the normal force.
Very good. So you're correctly following the sign convention, which you should. So it's going to be mg minus Fn in this case, and that is equal to mass times what?
The centripetal acceleration.
Centripetal acceleration. And since this is uniform circular motion, it's the same v everywhere, right? It's fixed speed. So it's just going to be v square divided by r again. That makes sense? So if you solve for Fn now, you get a different value of Fn. So Fn is equal to mg minus mv square over r in this particular case. So in this case, if you factor out the m, you get g minus v square over r. That makes sense? So in which position will the passenger feel heavier than usual?
At the bottom.
At the bottom, because there the normal force is greater than the person's weight. That makes sense? And at the top, the normal force will be less than the person's weight. The person's weight obviously is mg. You can see that Fn is less than mg at the top. So here the person will feel lighter. And here the person will feel heavier than usual. And they can also confirm that by just standing on a scale. And the scale, you know, it always just reads out the normal force. And so they will see that the normal force or the readout of the scale is greater at the bottom, and it's less than their weight at the top. That makes sense? Now, in a normal Ferris wheel, the velocity is very small. So this is not something the passenger would really notice because the velocity is so small. So v square over r will not be that much, right? And also the r is very large for a Ferris wheel. So v square over r will indeed be quite small. So the passenger will not notice. But there can be situations where a person is going around in a circle at a very high speed. And in that case, it's certainly noticeable. And that happens, before that happens, let me just quickly explain one thing. So the centripetal acceleration is v square over r. Now, if you have done this problem, which was much earlier in the PowerPoint, and I didn't work through it in class, if you've done this problem, you had to calculate an acceleration, and then I had you express this acceleration in terms of g. So that is usually a common thing that's done, because if I just give you an acceleration and tell you 3 meters per second squared, you won't know off the top of your head, is that a very high acceleration or is that a very slow acceleration? What kind of acceleration is that? So a convenient way of expressing acceleration is in terms of g, right? So if I tell you, instead of telling you that an acceleration is 4.9 meters per second square, if I just tell you that that's half of g, then you will have a better idea of how much acceleration that is, because you know the acceleration of a falling object, that's 9.8 meters per second square, that's g. So if I tell you half of g or 3/5 of g or 2 times g, that will give you a much clearer idea of how much the magnitude of that acceleration is. So it's common to express accelerations in terms of g rather than giving you the actual meters per second square. That makes sense? So so accelerations are often expressed in terms of g. Okay, so suppose you have a fighter pilot who's doing this particular maneuver where their plane is, so that's my fighter jet. Okay, so their plane is executing a vertical circle like this. So the same considerations would apply, and the force the force exerted by the seat on the pilot when the pilot is at the bottom would be given by Fn equals what we just calculated, mg plus v square over r, right? That would be the force exerted by the seat on the pilot. Now, let's calculate this v square over r with some typical numbers. So I've written down some numbers at the bottom of the slide. So suppose you have a fighter jet executing a vertical loop of 1,000 meters. and the speed of the jet, V, is 280 meters per second, which would be quite slow for a fighter jet, but we'll just go with these numbers. So in that case, what is V squared over R? So V squared over R would be, can somebody calculate that and tell me what you get for V squared over R?
784.
784. Can somebody, it sounds a bit on the high side. Can somebody check that? And
Oh, 78.4.
yeah. So that sounds more like it. So 78.4. What is 78.4 divided by G? If I want to express this as in terms of G. So what is 78.4 divided by G?
8.
8. Okay. So 8G, approximately 8G, right? Does it can somebody confirm that? Confirm the calculation?
That's what I got.
Okay, so V squared over R is 78.4 meters per second, but we saw that it makes more sense to us if we just write it as a multiple of G, so that's 8G. So we can see that that's quite a high acceleration, right? So if we plug that in and calculate Fn, so Fn is going to be mg plus 8G. So I'm writing the V squared over R as 8G. So that comes to 9 times mg. That makes sense? So the person will feel 9 times as heavy as they normally are. Fn is turning out to be 9 times their body weight. Mg is their body weight. So the person will feel 9 times as heavy as they normally feel. So that is tremendous. So now it's not just them feeling heavy and pushed into their seat, their entire body will feel heavy. As I was mentioning, if they try to lift up their arm will feel extremely heavy because it's 9 times as heavy as it normally is, right? Their heart will find that their blood has suddenly become really heavy, and their heart is having to work really, really hard in order to pump their blood to their brain. That makes sense? Which is a problem, because unless the blood is regularly supplied to the brain will go into blackout and the person will pass out, right? So fighter pilots are specifically trained to withstand these enormous forces. And sometimes these kinds of forces are called G forces. That's just a colloquial name. So this would be 9G. We would call this 9G. So fighter pilots are specifically trained to deal with these enormous G forces. Normal human beings will pass out at 2 or 3G. That's the maximum that normal people can take. They'll pass out because their blood will their heart will not be able to supply blood to their brain. So that's why they'll pass out. But fighter pilots can withstand. They're trained to withstand for short periods of time, 8G or 9G, so that they can still operate their plane and make critical decisions even in situations like this. That makes sense to all of you? And I'll just show you a video of fighter pilots being trained to do this. So they're put in these centrifuge machines, and they're asked to, there's somebody who coaches them through it. Okay, so this is going to take a little bit of time to load. And let me set the optimize for video clip. All right, so you can see see that this person is not having fun by just looking at his eyes.
1, engage. Legs tight, deep breath. You're on top, breathe. 1, 2, breathe. Drop the shoulders, breathe. 1, 2, breathe. Squeeze your legs, squeeze your butt. Hey, squeeze, keep squeezing, keep squeezing, keep squeezing. Are you there? How you doing? How you doing?
No.
You know what happened?
So you can see that this guy passed out for a little bit of time. If you watch this video, you can see many of the other trainees. Some of them pass out, some of them do really bad, and some of them are pretty strong. Particularly the girls are pretty strong. They don't pass out. All right, so that is a practical application of this. So if you're going in a vertical circle at a very high speed, then the G forces, or the normal force that's felt by you, which we are calling G forces here, can be really large. Have any of you been in one of those? What are they called? So you go into this circular thing and it whirls it around.
You mean a
And
gyroscope?
Yeah.
no, not a gyroscope.
Or the ones like at the
At the carnivals and fairs.
yeah, the
like
press
a
you
The
press.
gravitron machine, right? So it's a similar thing in a gravitron machine. So you are being spun around, and so the normal force on you, since you're being spun around, is going to be much greater. Is going to be quite large, right? And so you will feel pushed against your seat, and so you will not be able, and you'll find it quite hard, difficult to lift your arm or even sit up straight. So that is for the exact same reason. That makes sense? I went into a gravitron machine a couple of years ago for the first time in my life, because I've never been to any fairs or anything since I didn't grow up in this country. And so as I was being spun around, I did a quick calculation, and I saw that I calculated the v square over r. They told us that we are being spun around at 40 miles per hour, and I estimated the radius of the circle. So I did the v square over r, and I saw that it's going to be about 1.5 Gs. And even at 1.5 Gs, I was having a really hard time, moving my arms and stuff. So that's just 1.5 Gs. Anyway, so that's that problem. Let's do a similar problem. I'll let you read this. So there's a bucket that's filled with water, and it's swung in a vertical circle. So and the bucket is upside down at the top of the circle. So the question is, what is the minimum speed that the bucket should have at the top of the circle so that the water doesn't spill? So you can try this on your own. Just get a bucket or a cup or something, and if you swing it around fast enough, you'll see that at the top of the circle, if you're going fast enough, the water will not spill, right? So that the question is, what is the minimum speed necessary so that the water doesn't spill? So let's analyze this. Actually, let's just watch this video first, and then we'll analyze it.
So I think you're going to be just fine. And if not, gosh, was it fun seeing a meteorologist spin this over
And
her
I'm wearing
head.
white today. I'm so
Okay, you're going to
glad
be
I
great.
heard about
All right,
this
you're feeling
experiment
good?
before.
All right, good. So
Feeling
now
good.
here's what I want you to do.
Yeah.
You're going to get a little just kind of rocking action. That centripetal force, it's a center-seeking force. Ready? Kind of
Not
up and
even
over your
trick
head.
you.
One, two, three,
three.
up and over your head. Here we go.
Oh.
Nice. See, you did it. You did it. Go again. Come on. Be brave. Be brave. Nice.
Here we go.
Nice. Nice. There you go. It's okay. It's okay. That's
Water
just,
just
they're
went
just like,
everywhere.
they're just like.
All right. So the question is, what is the minimum speed that you must be spinning it at so that the water doesn't spill at the top, right? So let's analyze this. So here is our bucket, and here is the water. Okay, that's the water. All right, and the bucket is connected by a rope to this point O, and it's been the water is being water and the bucket are being spun in this vertical circle. Let's say that the radius really means radius all the way out to the water is r. Radius of this circle is r, and we're going to treat the water as a point mass. Radius is r. Okay, so let's say that the speed here is v. So our question is, what is the minimum speed v so that the water doesn't spill, right? That's what we're trying to analyze. Okay, so let's this speed just be some arbitrary v at which the water doesn't spill. So the water can still complete a full circle at this speed. It's not necessarily the minimum speed, it's just some speed at which it doesn't spill. Okay, let's apply Newton's second law to the water, and our system is just the water right now, okay? What are the forces that are acting just on the water when it's at the top?
Is there a normal force acting on the water?
Yes, exactly. Which direction is the normal force, and what exactly is exerting the normal force?
Never mind, I don't know.
Think about it.
Would it be radially inward because it's coming from the bucket?
Yes, it's coming from the bottom of the bucket. So the water is again, so whenever you're pushing against any surface, that surface exerts a normal force by Newton's third law, right? Perpendicular to itself. So right now, the water is in contact with the bottom of the bucket. And so the bottom of the bucket exerts a force on it, but the bottom of the bucket is above the water because the bucket is upside down. So the normal force acting on the water is in this direction, radially inwards. And that is simply because the surface exerting the normal force happens to be above the water. In this previous example, the surface exerting the normal force was below the system, and so the normal force was upwards. But in this case, the surface exerting the normal force, which is the bottom of the bucket, is above the water, and so the normal force is pointed downwards. That makes sense? What other force is acting on the water in addition to the normal force?
Gravity.
Gravity, exactly. So the other force acting on it is gravity. These are the two forces acting on the water when the water is at the top. That makes sense? When the bucket is in that topmost position. Is everybody 100% clear about why the normal force is pointed downwards here? Anyone not clear? Okay, all right. So now it's just a matter of applying Newton's second law. So Newton's second law, can somebody help me apply Newton's second law using our sign convention? Radially inward is positive.
Is it Fn plus mg equals?
Very good.
MA?
Excellent. Fn plus mg is equal to what should be on the right side?
MAC.
Yes, excellent. And can you remind us what AC formula for AC is?
Yeah, centripetal acceleration.
Yeah, what's the formula for that in terms of V and R?
V squared over R.
Very good. And that is our equation that we get from Newton's second law, right? Now let's think about what is the lowest that this V can be. That's what we're going to think about now. Now let's think about what happens when the water loses contact with the bucket and starts falling, right? So when the water starts falling, which of these two forces changes?
The normal force.
Yes, because if it's no longer in touch with the bucket anymore, bottom of the bucket anymore, then there is no question of any normal force. That makes sense? So once it loses contact, what's going to happen is normal force will become zero. That makes sense? So that is the point when the water is really starting to fall. It's not in touch with the bottom of the bucket anymore. So there is no normal force, right? So we can use that to calculate the minimum velocity necessary for the object to go around in a circle. So we want the velocity to be such that the normal force is just a hair above zero, not exactly zero, right? So we can set that we can say that the minimum velocity necessary to complete the circle would be when you set Fn equals 0. We are just looking at Fn equals 0 as the limiting case, but we really want the Fn to be a hair above 0, not exactly 0. So at that point, you're going to have mg is equal to mv minimum square divided by r, right? And so from here, we can solve for the minimum velocity. So the minimum velocity is going to be the square root of rg. Is that clear to all of you? This is a result that we'll use often in other chapters as well. That completely clear? And it's just a consequence of Newton's second law. So we use Newton's second law to write down an equation for the velocity of the object and in terms of the forces acting on it. And then we use the fact that when it's about to lose contact, the normal force will be 0. Right? And so we set the normal force to be 0 to get the minimum velocity that it must have in order to be able to complete the circle. And that turns out to be square root of rg. Okay. Any questions about this? That completely clear? All right. So that really concludes our discussion of circular motion. Okay, and this problem is exactly the same thing. So in a circular roller coaster, the carriage is upside down at the top of the circle. And what minimum speed must the carriage have at the top of the circle so that the passengers don't fall out. So the passengers are upside down, and it's exactly the same thing. It's going to be square root of RG, just the same thing that we derived. That makes sense? Okay. All right. This problem has an interesting follow-up, which we'll see in the next chapter. And I'll let you do this. We've already done most of this problem today. So that really concludes our discussion of chapter 5. And we're going to skip the rest of chapter 5. So as I said, tomorrow, we are not going to cover new materials. So tomorrow, 1 o'clock, I'll just leave it open. You can just come and ask me any questions if you have any. And so what we can do now, since we have more than half an hour left, is we can get a start with chapter 6 and see how far we can go. And tomorrow we are not going to have any lectures. I'll post a lecture that you can watch after taking the exam tomorrow. That makes sense? So let's just go ahead and start with chapter 6 and just at least cover the first few concepts. So chapters 6 and 7 are also very interrelated. So I cover them both in one PowerPoint because they're very interrelated. All right, so in this chapter, we're going to start talking about energy and work. So we'll talk about energy later on in the chapter. We'll start with work. So there's really no point in going over these definitions because they're not going to make any sense right now. But let's start with the definition of work. So what's going to happen in this chapter is that I'm going to define what work is, and we are going to look at some examples on how to calculate work. And most of it is going to seem really abstract. Yeah, so you'll be wondering in the beginning of the chapter, why are we defining this weird thing? And what's the point of doing this? Later on, that will become relevant. So how this relates to the real world will become relevant. But for now, this will just be an abstract concept. All right. So we're first going to calculate the work done by a constant force. The work done by a constant force. Suppose you have an object that's sitting on a surface like this, right? And there is a force acting on the object. And as a result of that force acting on the object moves from here to here. So this is the displacement vector for the object. And let's say that the angle between the force and the displacement vector happens to be theta, right? So then we say that the work done by the force F is given by W is the dot product of the force vector and the displacement vector. So remember dot products from chapter 1. So W is the dot product of the force and the displacement. Can somebody remind me what is the definition of a dot product? So in terms of the magnitudes of the vectors, the geometrical formula, in other words.
The magnitude of the first vector times the magnitude of the second vector times the cosine of theta.
Very good. That's exactly right. So the work done by the force F is given by F dot D, which can also be written as the magnitude of F times the magnitude of D times cosine of the angle between these two vectors, right? So that is the definition of work, but it's very, very, very important to realize that this definition is limited. There are two conditions which must hold for this definition to apply. That is one thing that students forget all the time. So this definition applies only if the following two conditions hold. Number one, the force is constant, which means it's not changing magnitude or direction. And number two, the object moves in a straight line. In a straight line. Very, very important to remember that. That clear to all of you? All right. Okay. So that is the definition of work. What is the unit of work? The unit of work, the SI unit of work is joule. And 1 joule, you can see that work is basically force times distance times cosine of the angle between them. Cosine theta obviously is a pure number. So the unit of work would be newtons multiplied by meters, right? So 1 joule is 1 Newton times 1 meter. That clear to all of you? So joule is the unit of work. We'll see later on that it's also the unit of energy in the SI system. All right, so a little bit of terminology involved here. So that is the work done by or against a force. So suppose you have this situation. The force is acting in this direction. The displacement of the object is in this direction. Same thing as what we had before. The work will be given by F dot D, which is FD cosine theta. Notice that I can write the magnitudes of the vectors also like this by just not putting the arrow on top. Okay, so in this situation, let's call this situation 1. Will the work done be positive or negative, do you think?
Will it be positive?
Yes, and how do you know it's going to be positive?
Because the cosine of that
Yeah,
angle.
because theta is an acute angle, right? The magnitude of F and magnitude of D are guaranteed to be positive because they're magnitudes of vectors. But theta is an acute angle. And so the work done will be positive. Right? And so in this case, we say that the work is done by the force. So whenever the work done by a force is positive, we say that work is done by the force. Clearly, that really means, in a very informal way, that the force is getting its way. Force is getting its way. You can see that the force is kind of trying to take it to the right, towards the right, and the object is moving towards the right. Not exactly in the direction the force wanted to take it, but still it's kind of moving towards the right. The direction of the force and the direction of the displacement is at least less than 90 degrees. So the force is getting its way, and we say that the work is done by the force when the work done is positive, right? Let's look at this situation. Suppose the force is now acting in this direction, but the object is still moving to the right like this. Can you give me an example of when that might happen? How could that be possible?
When the velocity is in the opposite direction of force.
Yes, so that is one way that could be possible. That just imagine that the object was already moving very, very fast to the right, and then suddenly you start applying a force in the towards the upper left. That force will have an effect, but it'll take a while, right? So for a while, the force would continue to act this way, and the object will continue moving in that direction. Another situation might be that maybe there is a much stronger force that's pushing it to the right. I didn't say that this is the only force acting on the object, right? So maybe there happens to be a much stronger force that's taking it to the right. And so this force is not having any effect on it. That makes sense? So when you have a situation like this, for whatever reason, let's calculate the sign of the work. So will the work done be positive or negative?
It would be negative.
Yes, negative because the angle between the force and the displacement is greater than 90 degrees. That makes sense? Whenever the work done is negative, we say that work is done against the force. So work is being done against the force. And negative work, as you can see, means that the force is not getting its way. Colloquially, that means, or very informally, it means the force is not getting its way. Is that clear to all of you? One last case would be, suppose the object is moving in this direction and the force is acting in this direction. Actually, I can give you a real life example of that immediately. What is the direction of the gravitational force on this object?
Down, straight.
Yes. So we can just use gravity as our example in this case. So in this case, what is the work done by gravity? Is it going to be positive, negative, zero? What's the work done by gravity?
Is it zero?
Yes. Why is it 0?
Because the cosine of 90 degrees. Is 0.
Exactly. So the direction, the angle between the force and the displacement in this case is 90 degrees. So the work done is 0. So gravity is not doing any work, or any force that's perpendicular to the displacement does not do any work. That makes sense? All right. So please make sure you're clear about what is meant by positive work, negative work, and 0 work. So 0 work can happen when there is either no displacement. So another situation would be, suppose the object were just at rest. The gravity is acting down like this. The object is at rest. So in this case, there is no work done because there is no displacement. Or there could be a displacement, but the force and the displacement could be mutually perpendicular, in which case there is no work done. That makes sense to all of you? All right. So, okay, so work done by a force means the force is getting its way. So just that's useful to just keep in mind. Okay. Now, a very important concept that we'll see a lot in the next couple of chapters is the concept of net work. So if there is more than one force acting on an object, then it's useful to define the network. The network just means the total amount of work done by all the forces acting on the object. So, and since work, now let me clarify this one thing. Looking at the formula for work, would you say that work is a scalar or a vector?
Scalar.
Yes. How do you know it's a scalar?
This work has no direction.
That is true, but is there any way of telling me that by just looking at this formula from something that we've learned in chapter 1?
The dot product usually results in a scalar.
Always gives you a scalar. That makes sense? Not usually, always gives you a scalar. So that's right. So the way the work is defined, it's the dot product of two vectors, and so it's guaranteed to be a scalar. That makes sense? We'll see later on that energy is also a scalar quantity. So work is a scalar quantity. And so when you're combining different amounts of work, you don't have to bother with directions and components and all that stuff. None of that applies to scalars, right? So if you're combining different amounts of work, it's just a matter of adding up the works, the different amounts of work. So to give you an example, suppose you have an object that's sitting on the ground over here, and there are two forces acting on that object. One of them is this force, F1, which is maybe 10 newtons. And then you've got another force, F2, which is at an angle. Let's just keep this angle simple. What is 90 plus 45? 135 degrees. So an F2 is also 10 newtons, let's say. And the object happens to move a distance of 1 meter. So this distance is 1 meter. So what is the net work done by both of these forces? So let's go ahead and calculate each one. So what is the work done by F1?
F1 times the distance moved.
Yes, it's going to be F1, which is 10 newtons, multiplied by 1 meter, multiplied by cosine of the angle between the direction of the force and the direction of the displacement. The displacement is from here to here. So the force and the displacement make a 0-degree angle, cosine of 0 degrees, which is 10 times 1 or 10 joules. That makes sense? That is the work done by F1. It's the work done by F2. So to calculate the work done by F2, you would do the same thing. You would take 10 newtons, the magnitude of F2, multiplied by the same displacement, 1 meter, multiplied by cosine of 135 degrees. Right? What is cosine of 135 degrees?
Negative square root of 2 over 2.
Yeah, negative 1 over root 2. That makes sense? And so F2 is doing negative work in this case. Does it make sense that F2 is doing negative work? The answer is yes, because F2 is not getting its way at all. That makes sense? So F2, the work done by F2 is negative, more precisely because the angle between F2 and the displacement is greater than 90 degrees. So F2 is, unsurprisingly, doing negative work. So it's going to be 10 divided by root 2 minus 10 divided by root 2 joules, right? What is that as a decimal? 10 divided by root 2 as a decimal?
7.07.
7 minus 7.07 minus 7.07 joules is the work done by F2, right? And so what is the total amount of work done? So W total will just be the algebraic sum of these two. So that's 10 minus 7.07. So that's 2.93 or something like that. Positive 2.93 joules is the work done by both these forces together. So that is the net work. That makes sense. I should write this as W net because that's the technical term. W net is equal to 2.93 joules. So when you're combining different amounts of work, you just algebraically add them because work is a scalar. That clear to all of you? All right. You can do this example on your own. It's worked out on the slide. All right, so let's take a look at this example. So this is a particular exercise called the barbell squat. It is the best exercise on the planet, the #1 exercise. It uses every muscle in your body. So the question is saying that during the descent phase of the squat, so just while the person is descending with the barbell on their back, what are the signs of the work done by the lifter and also by gravity? So you have to remember that while the barbell is being lowered, the lifter is still exerting an upward force on the barbell. So there are only two forces on the barbell. One is the weight of the barbell, which is acting downwards. But while the barbell is being lowered, the lifter is certainly not pulling the barbell downwards. They're still exerting an upward force on the barbell, right? Because if they pull the barbell downwards, they're just going to crash into the ground. So they are still exerting an upward force on the barbell while it's being lowered. And also when it's being raised, the lifter is exerting an upward force on the barbell, right? So the question is, you have to answer this question about the sign of work. So let me just put this up on top hat. Oh, I forgot to launch top hat. Just 1 second. All right, so it's on top hat now. All right, please put in your answers. Okay, so let's see what you guys did here. So let's see, the work done by the lifter is negative. Yes, so the correct answer is C. Let's just make sure that we are all on the same page regarding this. So we are talking about the descent phase of the squat. So that means the barbell is going downwards. The displacement of the barbell is in the downward direction. The force exerted by the lifter, as I just said, is upwards, but it's not as great as the force exerted by gravity, and that's why the barbell is descending, right? So the lifter is doing negative work because the force that they are exerting is in the upward direction. The barbell is going in the downward direction. And so the lifter is doing negative work and gravity is doing positive work because gravity is pulling downwards and the barbell is also descending downwards. And so gravity is doing positive work. The lifter is doing negative work. Is everybody clear about this? All right, okay. Yeah, this is a similar example, so you can talk about this. You can do this on your own. Let's try a problem on this. So I think I have this problem set up on, or do I not have it? Huh. I thought I had this problem on Top Hat. Anyway, I looks like I don't have it. Okay, so I'll give you a moment to think about this problem and see if you can set it up on your own. So this particular move is called the deadlift. When I first wrote these problems, I used to assume that everybody knows what a squat is and what a deadlift is. And then I found out that a lot of people don't. And so I include these videos. Actually, I didn't myself for most of my life until I started lifting a few years ago. All right, so so in a deadlift, you exert a force on the barbell and you raise the barbell to a certain height, right? So a power lifter deadlifts a barbell to a height of 0.85 meters. So the barbell is going up by that height of 0.85 meters. And then lowers the bar, applying a constant upward force. So while the barbell is descending, the force exerted by the lifter, and I'm just drawing one force arrow, even though the lifter exerts two forces with their two arms. So the force exerted by the lifter is upwards, but the barbell is descending in the downward direction, right? So you have to calculate the work done by the power lifter in lowering the bar to the ground. That makes sense? Okay, so let's draw this. What were the numbers? 365 pounds, 167 kg, and 0.85 meters. Okay, so the barbell is like this, and it's being lowered by a certain distance. And while it's being lowered, there is an upward force exerted by the lifter, and then there is the force of gravity acting downwards on the barbell. That makes sense? So we have to find out the work done by the lifter, work done by the force F. Okay, so the work done, first of all, we have to check whether we can use our formula for work. So can somebody quickly remind me, the formula for work is F dot D. Can somebody quickly remind me what are the conditions that must hold in order for this formula to be true?
If the force is constant and if the distance is in a straight line.
Yes. So in this case, both the forces, we're going to assume that the forces are constant. Actually, the problem should tell us that, but you can assume that the forces are constant because we simply don't know what to do if they're not constant. So the forces are constant and the object, the barbell, is moving in a straight line. So we are good to use the simple formula for work. So the work will be F dot D. All right. So that means that is the magnitude of the force exerted by the lifter, which we don't know yet. Then the displacement, which we do know, it's 0.85 meters, times the cosine of the angle between the force and the displacement. What is that angle?
Is that 180 degrees?
Yes, because the object is going downwards and the force exerted by the lifter is upwards. So it's going to be cosine of 180 degrees. Is everybody clear about that? So cosine of 180 degrees. What is cosine of 180 degrees?
-1.
-1, exactly. So it's going to be minus F times T. Just ordinary multiplication here, minus F times T. So it was F dot T over here, but then we use this formula. So it's just minus F times T. That is going to be the answer. The only problem is I don't know what F is. That clear to all of you? All right. So from this point, it becomes a chapter 4 and 5 problem, right? So this was the only part of this problem that related to chapter 6. So now we have to apply Newton's second law to calculate what the force is, right? And yeah, so that's what we need to do. So we have to apply Newton's second law to find out what the force is. And another piece of information that we are given is we are told that the barbell starts with a velocity v equals 0 at the top, and at the bottom it has a velocity of 2 meters per second in the downward direction. All right, so we have to use that to find out what the force is. So we'll write v equals 0 over here, and v equals -2 in our sign convention, meters per second, when it reaches the ground. So it reaches the ground with a speed of 2 meters per second. All right, so the question is, how do we find the force, right? We know that net force is equal to mass times acceleration, right? So maybe if we can somehow figure out the acceleration, we can use that to find the force, right? Is there any way I can find the acceleration?
Kinematics.
Yes, we can use kinematics to find the acceleration. So this is a great problem, a review problem for the exam, because we are covering everything in this problem that you have on the exam. So we are going to do kinematics to try to find the velocity, to find the acceleration. So we are told that the initial velocity is 0. So our plan is use F net equals mass times acceleration to find F. That's what we need in order to plug into the formula for work, and use kinematics to find A. All right, so let's do a kinematics problem. This is just a chapter 2 problem. So the initial velocity is 0 and the final velocity is -2. So what is the acceleration? How do I find that? Which equation could I use?
The one kinematics equation that doesn't deal with time.
Yes, which is v square, v final square equals v initial square plus 2 times the acceleration, y final minus y initial. That makes sense? So we can take y initial, y final to be 0, y initial to be 0.85. That's what it was, right? 0.85 meters, okay. All right, so let's figure out the acceleration. V final is 0. V initial is, no, V final is -2, sorry. So this is -2 square. V initial is 0. 2 times A is what I'm solving for. And Y final is 0. Y initial is 0.85. Everybody with me? Now, in this sign convention, do you expect the acceleration to be positive or negative without doing any calculations? Our sign convention is upward is positive.
Negative.
Yes, because the bar is clearly accelerating downwards, right? Because it's starting with 0 velocity, then it has a high velocity later on. So the acceleration is clearly in the downward direction. Everybody clear about that? So we would expect a negative answer for the acceleration. So let's see if that's what we get. So 4 is equal to 2 times A times -2 times A times 0.8. Somebody solve for A and tell me what you get.
I get negative 2.35.
All right, so can somebody confirm that? Negative 2.35 meters per second square. All right, very good. So you can see that the acceleration is in the downward direction, but it's not quite the acceleration due to free fall, which would be 9.8 meters per second square. That is simply because there is an there's a force in the upward direction being exerted by the lifter. If the lifter had just dropped the barbell, then its acceleration would have been 9.8 meters per second square. But in this case, since the lifter is still pulling upwards, it has a smaller acceleration in the downward direction. That makes sense? So we found the acceleration of the barbell. So now we can go ahead and plug this into Newton's second law. So F net equals mass times acceleration. So we are going to use the same sign convention. Upward is positive. Here is our barbell again. There are two forces acting on the barbell, F, the other one is mg. So in our sign convention, what is Newton's second law going to be?
F minus mg is equal to ma.
Exactly. F minus mg is equal to ma, right? And so so you would do, so if you plug in all the numbers, F minus the weight was 167, okay. 167 times 9.8 is equal to 167 times minus 2.35, right? Can somebody solve for F and tell me what you get?
I get 1,244.15.
Can somebody confirm that? 1244.45 you said? Okay,
Yes.
that's the force. That makes sense? So that is the force, and it's coming out positive in our sign convention, which is exactly what we would expect because it's an upward pointed force. All right, so now we have found the force, and that is the missing piece of information that we needed in order to answer the original question, which is the work done. So now we can just plug this into the formula for work, and we get work, which we found was minus magnitude of the force multiplied by the displacement. So that's going to be minus 1244.45 multiplied by the displacement, which was 0.85. And can somebody work that out and tell me what you get?
Negative 1,057.5.
1058 then joules. Is that clear to all of you? Yeah, so this one. That clear? So you can see that the work done will be negative here because while the barbell is descending, the force exerted by the power lifter is still in the upward direction. That makes sense? So the power lifter's force does negative work because it's not getting its way. It's pulling the barbell upwards, but the barbell is descending. That clear to all of you? All right, so I think we'll just stop here for today. Oh, this you can see that it has a very specific weight, 365 pounds. So the day I wrote this problem was the first time in my life I was able to do a deadlift for 365 problems, and I was on 365 pounds. So I was on cloud 9 and ended up writing this problem. All right, okay. Please make sure you understand this. And as I said, this is a good review problem for the exam as well, because we did kinematics and we also applied Newton's second law. And I think we'll just stop here for today. So this problem is very, very important. And this problem is a bit tricky. So I would, many students ask me whether the answer is wrong. The answer is given at the bottom of the slide, but it is not wrong. So try this problem and see if you can get the correct answer. There's nothing here that you don't know. It's just a slightly tricky problem. You have to be careful doing it. All right, so I think we'll stop here for today. And as I said, tomorrow 1 o'clock is an optional session. You can, if you have any questions about the slides or mastering physics, you can show up, or you can show up just to listen, and I'll just answer whatever questions people have. All right, okay. And the exam will be available at, I believe, around 4 o'clock tomorrow for 24 hours. All right, so if anybody has any questions, I can answer them. Otherwise, we are done. Okay, so I'll see you tomorrow.
Thank you.
Yeah.
Bye.